Hi, welcome back to part 2 of Enzyme Kinetics. We're going to continue deriving excuse me. We're going to continue deriving some of the enzyme equations, the most simple ones, under initial rate conditions, as we have discussed earlier. Under initial rate conditions, this will be true. And of course, we have our balances, as described before. And where we last left off, we wanted to talk about, rapid equilibrium assumption. That means the second reaction is pretty much a slow step or rate controlling step. So under equilibrium, this equation holds true because the forward and backward rate are equal. So forward and backward rate are equal. Or rather, this is the forward, this is the backward. So the backwards are equals to the forward rate. And so dEs of dt, as you can see here, dEs dt, that will equal to negative k2 into Es plus k1 times E times S minus k inverse Es. So since the forward and backward rates are approximately equal, you can just cancel this out. Now that simplifies the equation a lot. And immediately you can see that this is a ln plot, an exponential function with some kind of exponential decay with respect to Es. Now, the only problem is this: what is the concentration of Es and how can you measure it experimentally? Well, for that we have to look at our enzyme balance. This is the initial rate of enzymes concentration, and that will be equal to the, this is initial, let's write that there, initial equals the substrate, enzyme substrate complex, this is the concentration of that, times, plus the concentration of free enzymes. Okay, so we want to make this the subject, so we'll just rearrange our equation as so. Equals the E naught minus E, and that solves part of the question, part of the problem. But now you have this problem. What's E going to be? Well, thankfully we have our earlier equation to help us a little bit, so yeah, let's move on with that. So we have k minus 1 into Es, so k minus 1 into Es times k1 equals to k1 E, and the concentration of S. So let's go on making E the subject. It's E, now let's bring this to the other side, K inverse, alright, so there's a K inverse, the backward rate, into Es over K1, so just bring this over and bring this over, so divide that to both sides, and you'll have this kind of situation. Okay, so let's bring that back into our first equation. Let's substitute that back in here, and then you should sort of get a neater equation. Es equals to E naught minus K inverse over K1, and then Es over S. Okay? Well, now it's a little bit messy, so let's bring some things over. Let's bring this over here. So let's add this to both sides, and you'll get this Es plus K inverse over K1 Es by S, and that will equal to E naught. And then just more mathematics, you factorize that out. 1 plus K1, or K minus 1, K1, 1 over S. Okay? And now we can make ES the subject and so eliminate ES very quickly. E naught over 1 plus K1, K minus 1 over K1, 1 over concentration of S. So let's make it a little neater again, and we'll have this. So let's multiply S, concentration of S, to both the top and bottom. Over 1, or rather now over S, plus K minus 1 over K, 1, and that will be your derivation of ES. So now you have eliminated ES basically, and well, well, you don't want to keep writing K's, right? So let's make it neat over here. We'll just represent this as Km prime. So Km prime is some kind of rate constant. Just whatever the kind of mess you have there. So we don't have to keep, writing the same thing over and over again. Now let's just call this some kind of a rate constant. And now let us substitute that back into our equation, our initial equation, which is this. So from this, you can quite easily see that d of ES dt equals to minus K2 into ES. And of course, you just do the simple integration. Equals minus K2t. And then you just integrate. Right? And then you will get a ln function. So this is t equals 0 to t equals to time t. So this ES at 0 at t equals 0, ES t equals to time t. So you will have some ln of ES ES at time 0. So this is ES at time t, this is ES at time 0. So that will be equal to K2 at whatever time t. Okay? Not a problem. So now let's put this back. Let's substitute this back in here and let's see what we get. Okay, so next step, let's just do the substitution. ES equals to E naught S plus Km prime rather, and then we have this ln of ES at t over the initial concentration of ES equals to minus K2 t. So what is the so-called initial concentration of ES? Well, that seems to be, negligible, right? But okay, maybe I've gone off a little off tangent. Yeah, I should have done something a little earlier. Ah, okay, I see. Oh, never mind. Yes, anyway, I think I've gotten a little off tangent. Basically, you shouldn't be deriving, how ES change with time. I got a little carried away, I'm sorry. Anyway, we should be finding what this V is. So V equals to K2 into ES. So V equals to K2 into ES. Yep. But technically speaking, we can still use some of our whatever we've derived before. So we just substitute this in. So dp dt, that's the rate of generation of product, equals to K2 into E naught S over S plus Km. Okay? Okay, so what do we do next? Yeah, what do we do next? So yeah, we can see that this V is dependent on the substrate S. And of course this Km, which is the, in our case, dependent on the equilibrium constant. Of course the initial concentration of enzymes. That kind of makes a lot of sense. And let's say there is a case where, you know, E naught equals to ES. That means basically all the enzymes are filled with a substrate. Because all enzymes have been converted into enzyme substrate complex. Well, what would that mean? This means that if everything is becoming a enzyme substrate complex, that means the rate of production of P will be very fast, because that is when the ES concentration is the highest. And this is of course the highest it will ever go. So that means that Vmax will be reached when E naught, the initial rate of enzyme concentration, is equals to the current concentration of enzyme substrate complex. Alright? Because if this is maximum, then this is maximum. So the maximum it can go, Vmax equals to K2 times E naught. This will be the expression for Vmax. And what does it look like? It looks like this here. So another way we can write this rate of production of P is equals to the maximum rate of production of P times S, concentration of S, over this denominator here. And that's what we have for our rapid equilibrium assumption, where the second reaction is rate controlling. So, yep, that's about 13 minutes in. Thanks for watching. I'll see you in the next video. Goodbye.